Okay, work is a way to give energy to an object. I think we sort of said this implicitly in a few different ways, but I want to do it a little bit more explicitly. Let's say that we have an object, and our particular object has an initial velocity, we'll say v1, equal to 0 meters per second. And we apply a force to this object, F applied, of 5.00 newtons to the right. And then at some time later, while I continuously apply this force, the object later on, we got our v1 equal to 0 meters per second here, later on it has some other velocity. Let's say that I do this over a distance from here to here. Delta D equals 20.0 meters. First of all, let's figure out how much work we did to this thing. Same old equation, work equals force times delta D times cosine of theta. And I should say we're making a simplification here where there's no friction. So we're not going to talk about friction robbing energy from us. Let's just talk about this being an energy that's being given to this object by some pusher. So we could put it on wheels. Perfect wheels on a perfect ground. Must be physics. Okay? So we're doing work to this thing. First of all, if the displacement is in the same direction as the applied force, cosine theta just reduces to 1 because the angle between those two vectors is 0. The applied force is 5.00 newtons, and the displacement is 20.0 meters. We get 100 joules of work. Okay, nice round numbers. Now here's where it gets a little bit different. And we can talk about how to convert work into kinetic energy. We talked briefly about work being converted into gravitational potential energy, but let's talk about getting work to convert into kinetic energy. I got to make use of a kinematics energy equation first. Okay, so it's all well and good to say that work is equal to force times displacement, and we'll just leave off the cosine theta. But then I want to throw a little bit of kinematics in here. So mass times acceleration times displacement. And according to a kinematics equation that we said previously in our last unit, or 2 units ago I suppose now, acceleration times displacement could be rearranged to be equal to v2 squared minus v1 squared over 2. That's a rearranged version of an old kinematics equation that we've talked about. And I could say, hey, look, there's an acceleration times displacement here, and there's an acceleration times displacement here. Those guys match up. Let's sub that expression into the acceleration times displacement. So I'm going to say, all right, well, the work that I do on something is also equal to its mass times, all in brackets, v2 squared minus v1 squared all over 2. And I can do a little bit of simplifying here. I can say, all right, well, this is the same as saying mass times 1/2 v2 squared minus 1/2 v1 squared. And I can do even more simplifying, and I can say, all right, that work is the same as saying, and you'll forgive me if I do a little bit of rearranging as I do this, multiplying through. I'm going to multiply the m through the binomial, and I get 1/2 m v2 squared minus 1/2 m v1 squared. And so what I kind of have at this point is an expression that says, if I do some work on something, I've got a change in energy. Some energy that has to do with its velocity at the end, minus some energy that has to do with its velocity at the beginning. And people say, hey, well, that's kind of like, well, that's kind of kinetic energy, isn't it? They say, well, this must be the expression for the final kinetic energy. And this must be the expression for the initial kinetic energy. So the difference between those kinetic energies has to be the amount of new energy that I gave this thing. You know, there's a subtraction sign there, right? So that's a difference. The difference between these two kinetic energies has to be the additional work energy that I gave that thing. Okay? So EK2 minus EK1 is the amount of work that I gave it. Or people say the amount of work that I do on something is equal to its change in kinetic energy. Now getting back to the question that we had just a second ago, I'm going to put a box around this. That's a nice formula. That's a nice formula. And you know, if I want to have an equation for kinetic energy all by itself, the general equation for kinetic energy is just 1/2 mv squared. Okay? And that's a nice formula. Anyways, as I said, getting back to the question we were just doing. If we want to know what the final velocity is for this thing, we could use this. Change in kinetic energy is equal to 1/2 mv2 squared minus 1/2 mv1 squared. In this particular scenario, going all the way back up to our initial givens, v1 is equal to 0. So the second part of the equation disappears in a puff of 0. Because the v1 is a component of that formula, and so 0 times anything makes the whole formula equal 0. Okay? And so now we're left with change in kinetic energy is just going to be equal to 1/2 mv2 squared. Or we could say, well, the change in kinetic energy is really just work, right? So I can say work is equal to 1/2 mv2 squared. And I want to divide both sides by m. Take the m down to the bottom. Multiply both sides by 2 to get rid of that 1/2. And I suppose we probably want to square root both sides before the end of the day here. And so after all this mess is done, we've got a new expression that says that v2 is equal to 2 times the amount of work over the mass, all square rooted. Now I've worked myself into a corner here, so I'm going to have to get rid of this page in a second, so I'll wait for people to catch up. Because I do want to figure out what the final velocity of this object is. All right, can I take the page away now? Okay. So keeping the same values from before. We say V2 is equal to square root of 2 times the work divided by the mass of the object. And in this case, we said that the work that was done on this object was equal to 100 joules, according to our math, divided by the mass, which we claimed earlier. Did we claim a mass on this object?
No.
Oh, we haven't claimed a mass on this object. Okay. Let's go back and add to the diagram. Mass equals, oh, what's going to be a nice one? 20 kilograms. Let's make this a 20 kilogram object. Sorry, I forgot to write that in. 20.0 kilograms, all square rooted. So 2 times 100 is 200 joules, divided by 20 kilograms. Now, if we're being really good about our units, you remember that joules are equivalent to kilogram meters squared per second squared. We mentioned that last day. It's a derived unit, so we could say 200 kilogram meters squared per second squared all over 20 kilograms. Now the kilograms are going to cancel out. 200 divided by 20, not such a big deal, that's just 10. And it's 10 meters squared per second squared. Now square root of 10, that's going to take a little bit of thinking. What's the square root of 10? 3.12, what's that?
3.16.
Oh, 16, thank you.
22.
Yep. I'm going to stop at 7.8. Okay, that's good. That deals with the numbers part. What's the square root of meters squared per second squared? Meters per second. See, the units all work out. Isn't that nice? So we've got a final velocity for this thing. Well, we have a final speed. To look at the velocity, we'd have to go back and look at the original picture and say, oh, well, it's to the right. But we have a final speed. And that's the nice thing about energy. It's all scalars. It's all just magnitudes that we're dealing with. That's if you start off with zero velocity. Can I show you what happens if it starts off with a non-zero velocity? Well, I'll just sketch it out very quickly, okay? So we had the same scenario. We start off here. We finish off over here. You start off with velocity of some non-zero value, like 5, oopsie, velocity 1, blah, 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 blah. Velocity 1 equals 5.00 meters per second. And we end up with some new velocity, I don't know what, but I assume if there's an applied force on this thing, and I'm going to do my force vectors in black. This isn't really a true free body diagram anymore, we know that. F applied equals, we said it was 5.00 newtons. It's going to pick up speed. It still has a mass of 20 kilograms. And it still has a displacement of 20 meters. If I want to figure out what the final velocity would be, we can come back to our equation that we figured out just a minute ago. We could come back to the amount of work that you do on something is equal to the change in kinetic energy, 1/2 mv2 squared minus 1/2 mv1 squared. And that's really the same thing as talking about your change in kinetic energy, strictly speaking. The problem is now I can't say that the initial kinetic energy was equal to 0. That's not right anymore. So what I can do is take that initial kinetic energy over to the other side. So now it's the amount of work that you started out with minus, or that you're performing rather, the amount of work that you're performing, plus 1/2 mv1 squared is equal to 1/2 mv2 squared. So the first time we really cooked it, we made it start from rest, and that makes a lot of things simplify if you add in zero values. This is a little less cooked. If I want to get that final velocity, now I have to multiply both sides by 2. Divide both sides by m. Cancel, 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 cancel. And of course, square root both sides to get rid of that v2 squared value. And you end up with a somewhat ugly expression. Somewhat ugly. More ugly than before. v2 is equal to 2 times the amount of work plus 1/2 mass times v1 squared all over the mass, all square rooted. But you can still get the final velocity of this thing, even if it doesn't start from rest. It just takes a little bit more work with plugging in your values and maybe doing a little bit of rearranging. Do you want to do it? You want to plug in some values and see if we can do it? What the heck? Paper's here. I'm going to pause though because my timer's going to run out.